Hello and welcome. Identifying operational deflection shapes with optical 3D metrology. That's the topic of today's webinar. And I want to start with GOM's understanding of operational deflection shapes, or what we think. So we see the actual measured response of the component, or in general the object under test, is what we can derive from Aramis. And we see this is the operational deflection shape. So we measure the component under a forced motion during a vibration analysis test, and we capture, let's say, the amplitudes of the deflection on the structure. So we measure ODSs, and these can be used, of course, to compare to the simulated or calculated mode shapes, or to derive model parameters from this measurements. My name is Dominik Nielje, and I am happy to host this webinar together with my colleague Markus Klein. Markus Klein will answer your questions in the Q&A section of the WebEx tool. So if you have any questions, please drop them to the GOM host, which is present under the panelists. Let me start with a question that we got asked often in the past, and the question was, what kind of measuring data can digital image correlation provide for my vibration analysis that I want to carry out? And the answer to that question is that digital image correlation can provide precise measurements of displacements in 3D. So as we always work in our sensors, or typically work with a stereo camera setup, we can measure 3D coordinates via the principle of triangulation. And to triangulate 3D coordinates, we can use two methods for preparing our testing objects. So on the one hand, we can prepare our objects with measuring points, which are stickers, and these can be identified in the images, and you get one 3D coordinate for each measuring point that you place onto your object or your component. On the other hand, we can also work with a pattern-based approach that uses the black and white color pattern information that we apply onto the part by spray painting it, and we can use it to match corresponding areas in the left and right camera image, and thus also get 3D coordinates over time. So that means Aramis measures dynamically depending on the camera speed that is possible, and from these dynamic 3D coordinate measurement we can derive 3D displacements with a high temporal resolution for the vibration analysis. To give an idea what we can do with optical metrology in the field of vibration analysis, I want to share 3 application examples at the beginning with you. And the first is a polymer component that was excited with a harmonic frequency. So we can see, let's say, the component, we can see here the component on a shake table, and you can directly see, let's say, that we can derive from the Aramis measuring report on the one hand the operational deflection shape. So this is the information that you can see in the video to the left on the measuring report. So we can see, let's say, the displacements, the amplitudes by means of the color plot, and to the right we have our plot of the amplitudes of these 2 points, let's say, that we see placed on the object, so point 1 and point 2. This test was done to let's say, on the one hand validate the calculated mode shape that was derived from the simulation software, and the question behind the test was, does the real operational deflection shape look like the mode shape that was simulated? and of course to answer the questions, how much is this structure actually moving? What are the amplitudes on this component? We use the displacement information over time that we gathered with our RMS system to feed it into a frequency analysis. So here this was the input file, or in the diagram you can see the envelope curve of all these displacements that we measured on the measuring points in all three spatial directions, and this was exactly the information that we handed over to the vibration analysis software tool to get our frequency response curve. Also here we can see the envelope curve of the Fourier transformed displacements of all points in all three spatial directions. In the diagram, or in the frequency response diagram here, we can clearly see the peak here on at a frequency of 287 Hertz, and this was exactly what was also predicted or expected from the analytical analysis or mode shape calculation from the simulation. The amplitudes at this resonant frequency are in the range of 1/10 of a millimeter, what also validates our measuring results that we have seen in the first slide with the RMS measuring report, where we had amplitudes in the range of plus minus 0.25 millimeters. If we go further on with the analysis and use our data, we can also visualize the operating deflection shape. You can see here in the diagram that the information was used to calculate the operating deflection shape, and in this way you can derive a good comparison, let's say, to the mode shape that was calculated, and also answer in the end the question, how much is the structure really moving at a given frequency or at a particular frequency. Going from harmonic excitation to another type of vibration related testing, I want to share a door slam test with you. So this test is very common in the automotive industry, and primarily this is done to ensure the proper function of the door lock and also the door sealing system in reaction to a misuse basically by the car owner. So the door is slammed into the frame, and we can see here the actually measured response of the door assembly, or the outer panel to be more precise, the reaction to this impact event. So as you can see in the video, we have prepared the testing object on the one hand with a stochastic black and white pattern to derive data with a high spatial resolution in full field on the displacements here in the y direction, which is the more or less the front axle direction in the car coordinate system. So we can see, let's say, how the outer door panel indents or wobbles, let's say, in reaction to this impact event. Combined, this measurement was with also points that we placed on the chassis around the car door itself, so that we were able to calculate a rigid body motion compensation later on in the post-processing. Here again we can see the envelope curve of all the displacements in y direction. This was the dominant displacement behavior that we wanted to analyze. And if we take a look, let's say, on our frequency response curve that we got from our analysis tool, you can see where we have peaks in our frequency response, and to the right you will see the corresponding operational deflection shape at these frequencies. So the tool, I will go into detail later on a little bit more. So you can, it's an interactive tool, and you can, let's say, click on the peaks that you identify in the frequency response curve, and the 3D diagram will display and visualize the corresponding operational deflection shape. So here in this case we had multiple local maxima in our frequency response curve, so we could identify several interesting operational deflection shapes with our measurement here. The third example that I want to share with you comes from a rotating component in operation. So as we work with a non-contact measuring technique, we can also capture movements, motion information from rotating objects, like from this cooling fan of a truck that you see in the video over here. In the back, this is the RMS sensor that captures images with 1000 frames a second. And good thing about optical metrology here is that you don't need to capture any information on the rotational position of the component itself, because you can derive this kind of information directly from the measurement of the coordinates and the displacements with RMS. The video that you see here shows a typical result that you can generate and derive from RMS. So we have our homologous points, let's say, that we track over time, so we can group individual measuring points together to represent parts or parts of the component or assembly, to be more precise. And with this we can then track the whole part over time and derive displacement informations. So we just started this fan up and took a look at the displacements, and we used the center hub of this ventilator to also then calculate a rigid body compensation. So we see here, let's say, again, the envelope curve of all the displacements that we captured on the blades of this ventilator related to the center hub, let's say, so the deformation of this the ventilator in itself. When we fed this information again into our operation deflection shape analysis tool, we identified a peak at around 83 Hertz, and we could clearly see there's operating deflection shape connected to this frequency here. One is in plane, let's say, this rotational deformation of the points on the fan blades related to the center hub, and the second part of this operating deflection shape is an out of plane deformation, a wobbling, so to say, of the blades to the center hub. So when we discovered this by accident, more or less, we took another measurement and took a hammer impact test to analyze this assembly for its eigenfrequencies or mode shapes. And there we could see, let's say, okay, there is a mode shape at 85 Hertz. So we accidentally, let's say, in the testing that we did with the operating fan, we came close to the frequency to bring it into resonance. So here we can see the result coming from the hammer impact test, and this validates basically what we measured also in the operating state of this component. So now that we saw what we can do with optical metrology in the field of vibration analysis, I want to go over and mention the benefits that we have with our measuring technology. So the application examples showed these benefits. So on the one hand, we have a non-contact measuring principle with optical metrology. So already the setup of the test rig or the testing object preparation itself is much faster, let's say, as compared to the wiring of all individual accelerometers that you typically know from your test setups for vibration analysis. We have a fast setup and calibration of the sensor, and once you have placed, for example, our measuring points, which are ultra lightweight stickers in the end, you're basically ready with the preparation, ready to go. As these points are durable, you can also use it for repeatable measurements and use the same setup, so the sensor stays calibrated and you can do measurements in a row with it. Also good for the handling and the operation of for the test engineer itself are the compact dimension of the sensors. So you have seen in the video, let's say, what the sensors look like to be able to measure in 3D based on points or based on pattern. One of the biggest advantages that we have with our measuring technique is that we can measure many points in 3D synchronous. So we always capture this information, let's say, on all points at the same point in time, and each of these measuring points delivers 3D information, so acting as, let's say, 3 accelerometers for one sticker that we need to place on the testing object and the test rig. You've seen in the example before, we can also measure rotating components with optical metrology, as we do not have to touch and wire sensors. There's no problem in measuring rotating objects. If you want, you have the possibility to also include the excitation information in your measurement. This can be done on the one hand with placing either these measuring targets on your shake table or on your device that induces the excitation, or of course you have the possibility to also sample an electronic signal, a voltage signal that gives an information about the excitation. We can pass on, let's say, our measuring results via a digital interface over Ethernet connections with our tracking feature. And another big point, let's say, for our solution is that you can compare your measured operating deflection shapes with your simulated data in a full field way. We have seen, let's say, 3 examples of using optical metrology. In all these examples, we used the Aramis SRX sensor for the measurement because this is exactly the right choice for vibration analysis. This sensor combines a high resolution of the camera chip with the possibility to have high image capturing frequencies, so you can go up to 335 Hertz with full resolution, and then you have the possibility to crop, let's say, the image on the chip to increase your speed. So you have the possibility to go, let's say, narrower, or you have the possibility to use a predefined HD mode, which is able to capture images at 1000 frames a second at HD resolution. So this is the sensor that we use to capture all these application examples that you've seen before. If you need to go faster, let's say, than 1000 Hertz, 2000 Hertz, of course there's also the possibility to use high-speed cameras, for example, coming from Photon or phantom cameras, and use this one for digital image correlation with Aramis. Or of course you have also other sensors if it's lower excitation frequencies that you use in your test. Now let's have a look at the actual workflow that is behind the results that you have seen in the application example. So I want to show you how do you get from 3D measuring data to operational deflection shapes in Aramis. So to start with, of course, we have to do our measurements with the RMS sensor to capture the images. We will choose our measuring frequency according to Nyquist theorem to be 2 times the maximum expected frequency of vibration. If you have a harmonic excitation in your vibration test, you can also use a subsampling in this case and record images for a longer time to capture all information that is needed. As you have seen, you have the possibility to use either points or a pattern-based approach. There are, of course, advantages and disadvantages with each of these ways of preparing. So the points are very easy to apply, so this is done in some minutes, and they are very good on, let's say, highly structured parts. We have a lot of holes and let's say fins and stuff like that. And of course, if you cannot spray paint your part because it's too sensitive, then the points are the way to go for the preparation. Pattern works very good on smooth surfaces, and they provide a bit better accuracy and a higher data density, let's say, so you get more measuring points and results on your component. After the measurement, we have to go on with the post-processing of the data or the evaluation. The 2 steps, let's say, that you see in bold letters here are the ones that you need to do at minimum. This is what you really have to do. So we have to start and create what we call a point component or a surface component. So this is our matching information to identify either the same points in all images that we took over time, and or all these matching pattern information in the end to derive the 3D information. After that, we can transform our measuring data into a defined coordinate system. This coordinate system can be derived, for example, from a CAD file or from an FEA model that you already created, or you can use, let's say, the shape of your part itself and apply a 3-to-1 transformation. Depending on the test setup that you did and the analysis you want to derive, you can also apply the rigid body motion compensation. For example, as we have seen in the door slam example, we used there the chassis to compensate for the rigid body motion of the whole car and to analyze and focus really the indentation of the outer panel of the car door related to the frame or the chassis itself. So this is possible. Then we have to check our created software elements on the displacements, obviously, and this information then we can give on to other tools, vibration analysis tools. And if you like, of course, you can also carry out other advanced post-processing analyses in the RMS software, like deriving a 6 degree of freedom analysis. You can create sections, of course, and use or create geometric elements like best fit planes, best fit shapes, spheres to use for alignment or further evaluations. The next step in the workflow is to export our information, so the geometry information and the data on the displacements in the universal file format. We have this export feature directly in the RMS software, and it supports all directional displacements, so the x, dy, and dz of any of the following software elements, so surface components, point components, and sections. After that, we can import this UFF file into basically any of the vibration analysis tools that are available on the market. So we have documentations for workflows, how to handle these UFF files in the software's Emiscope, for the software of Burel and Kier, the BK Connect and PAC. But we also, of course, you can use other external tools. For example, you can work with NumPy and of course MATLAB, Pulse, LMS. All these all these tools support the UFF format. So then I want to present you this workflow also live in the RMS software. And for this presentation of the workflow, I chose measuring data that we captured on our generic GOM demo object. So this is a polymer component that is reinforced with glass fibers, and we subjected this component to a hammer impact, and during that hammer impact, let's say, the component was fixed in a clamping fixture at this position or at this area here of the part. We took measurement. We took images with the RMS SRX sensor at a frequency of 1000 frames a second, and the target was, of course, to determine the eigenfrequencies of that component. So then I will change over to the RMS software. In the 3D view, we can see the camera images. You have the possibility to switch between the camera images that were recorded with the left camera and the right camera by clicking on this icon over here. If you want to go through the time history of the test and see what has been recorded, for example, you can switch to time display with the timestamps over here, and then you can scroll and move through the stages, through the time history, by clicking and dragging this cursor over here. For the calculation of the ODSs, I want to start with the creation of so-called components. With these components, we will use the image data and calculate our 3D coordinates, or the measured 3D coordinates. So in this case here, I will use the surface component as we have prepared the measuring object with a stochastic color pattern of white and black color. I will select the area of interest on my part that I want to evaluate in the analysis, or that I want to calculate the ODS of. I will create a first component here and a second one on the inclined area of the component and the plateau over here. Right click and confirm my selection. Then I will click on the door icon for create and close, and the software will start with the matching algorithm to calculate the 3D data from the images. We will have the raw surface information as a first and basic result from the measurement, and let's say if I turn the images here, we can see the calculated 3D data. Now I want to transform this 3D data from the original coordinate system that comes from the sensor calibration procedure into a defined coordinate system that uses the shape of the part to define x and y direction, or the xy plane, and the z plane to be perpendicular to this lit area over here. So I will select the 3-to-1 alignment procedure, and with that feature I can click first 3 points from my 3D data set, and then 2 for a line, and the last one will define the origin of the new coordinate system. And with this we have the z direction defined as the out of plane direction of this lid over here. So this is what I want to achieve. I will say OK here. And as a second transformation operation, I will use a rigid body motion compensation. At the moment we can see, let's say, the overall motion reaction of the whole component, but I want to focus, let's say, on this lid area over here and see also the deformations of this lid relatively to the rest of the component. So I will fix the surface component 2 via a best fit algorithm, so that we subtract or compensate for the rigid body motion using this information here. And then we can see, let's say, the deflection, the deforming of this lid here relatively to the part which is called surface component number 2. To calculate the displacements in z direction, I will select this the surface component and use the inspect tool and call or inspect it for the displacement in z direction. And then we have, as a first measuring result here, we have the displacements in z coded by the color that you see here, corresponding to the magnitude of these displacements. If you want to take a quick look onto the deflections or the amplitudes of this z displacements, you can create, for example, so-called point inspections. I will place 2 points in these positions here, confirm the position, and then check them also for the displacement in z direction. Having done this, we can take a look, let's say, at the graph, let's say, that plots the amplitudes of this reaction of the 2 points, basically in the over time. Now I want to export, let's say, this measuring data into the universal file format to be able to post-process the data in third-party vibration analysis software tools like Emiscope, PAC, LMS or MATLAB, for example. So I will select the directional displacement check that was created on the surface component number 1. You can also double check by looking into the Explorer here that this element is selected, and then go to File, Export, Geometry, and then choose the option for Universal File Format. Then this pop-up window appears and you have several options or settings that you can enable or disable, and which settings to take depends mainly on the your vibration analysis software tool that you use, or which it is. Here in this case I will, let's say, go further with the single file option. If you want to have more detailed information on which settings are the right ones for your vibration analysis software, you can take a look into the GOM service area. There will be documented workflows for the most common vibration analysis software tools available. So I will confirm and export the data with pressing OK. And then I just want to show you the raw text file in the universal file format that is exported here. So the software automatically sorts the data into the right blocks according to the UFF file format convention, and we have the information of the knots and the meshing information, as well as the signals on the displacement in Z direction. So with this data you would be able to go further and calculate the operating deflection shapes in your vibration analysis software. As I mentioned before, GOM has also developed a visualization tool that can also calculate and display operating deflection shapes. To use this, we have made a connection, or we use the interface to the external Python interpreter. So you can go to python.org and download let's say the latest interpreter, and in the software here in Aramis you can make use of this interpreter if you select in the software settings the option for scripting and then use external Python interpreter, specify the path where this the executable file of Python can be found, and then you can work with this in this script that we that was developed by GOM. This is used, and the libraries like NumPy and Matplotlib are integrated in this script. To work with it, you have to select a surface component or a point component that you created here in Aramis, and then you can go to scripting, script choice, and start and run the get operational deflection shape script. This will now use the measuring data on the deflections and the shape information to calculate on the one hand the envelope curves on all displacements of all points in the three spatial directions x, y, and z, and also to carry out the Fourier transformation to have the frequency response curve. And it is an interactive tool, so you can change in between two modes of displaying the data. If you work with points or with a mesh-based data that is typically coming from the pattern prepared parts, so you can change here the display for the 3D diagram. And then if you go through this frequency response curve, you can click on the local maxima on the peaks here, and in the 3D diagram you will get the corresponding operating deflection shape as a display. As I said, it's interactive, so you can also enable and disable the individual envelope curves here for the directional displacements. For example, I can disable the Z component of the displacements, and the same is true here for the frequency response curve. So here in this case we had, let's say, a clear peak here in the beginning, let's say 20 to 30 Hertz, a clear bending influence, but also modes of higher order, let's say, are present and can be visualized with the operating deflection shapes by clicking onto the peaks here. So this is a showcase to exhibit what is possible with using the external Python interpreter and the libraries. Okay, so this is the workflow in the Aramis software to derive operational deflection shapes. So let me go back to my presentation. We have seen this workflow here as an outlook to what is also possible. I want to mention here the full field comparison of the measured ODS that we have seen. You can derive it from Aramis, and then you can also compare it to your simulated ODSs or mode shapes in a full field way. So we have the possibility to import FEA data, and you can also carry out this kind of comparisons or in a first visual inspection. So all this stuff that you have seen now in the webinar will be made available. So there will be recordings posted on our YouTube channel. And if you have an interest in the example script that I showed you and used during the live presentation, you can get it if you register for free in our GOM service area. So this is where you get all these informations later on. You will also get an email after this webinar with the information where you can directly find it. So that's the end of the webinar today. I would like to thank you very much for attending this session today. I hope you enjoyed the information that we wanted to share with you, and we are happy for your for getting your feedback. So if you have ideas, please let us know, and yeah, enjoy your coffee break. Have a good day and goodbye.